Are you recording? Nope. All right.
Light's like a transverse wave. Larger amplitude gives us larger brightness. The top of a transverse wave is called the crest, and the bottom trough is called the trough. Now, how spread out the waves are can be measured from any analogous points on the wave, meaning from crest to crest, from trough to trough, or from this point you measure a hole down and a hole up, or a hole up and a hole down. And then you can find how long a wave is, which we call the wavelength. And wavelength is, the symbol used for wavelength is the Greek letter lambda there. And it's not complicated. GTH is the Greek letter lambda. And it's literally like if you could see the light waves, if you could stop one and hold it still, like this transverse wave holds still on the board, and then you took a ruler and measured from crest to crest or trough to trough, you would literally be able to measure that light in meters or millimeters or nanometers. It's just a length. Like you measure your own height, you can measure a wavelength. And visible light is usually measured in nanometers. That's 10 to the negative 9 meters. So like a millimeter is 10 to the negative 3, a nanometer is 10 to the negative 9. So the visible light, the range of visible light that we can see is very small wavelength. Ryan? Yes. Okay, so we've had kind of sound on our minds, and light has a lot of similar characteristics, right? We have an amplitude that tells us brightness, whereas sound amplitude tells us loudness. Pitch for sound has to do with wavelength. And what, therefore, do we see light having to do with wavelength? What characteristic of light is determined by wavelength, Joshua?
If we can see it.
If we can see it. And the parts of light we can see, Joseph?
It determines the color.
Color. Okay, so wavelength or frequency, which we know is the inverse of wavelength, helps us determine what color we're looking at. And if it's not part of the visible spectrum, then the characteristics of the wave. Is it a radio wave, television wave, microwave, infrared wave, gamma wave? All of those are, just like light waves, part of the electromagnetic spectrum. Right? So there's part we can see, and then parts on either end of that we can't see. But they're all electromagnetic waves. So light is a transverse wave. So I could go even further with that and say light is electromagnetic. Light is an electromagnetic wave, or you can say electromagnetic radiation. And the visible spectrum and all the other types just go in one kind of continuum based on wavelength. So, does sound from last week need a medium through which to travel?
Yes.
Yes. How about light?
No.
No. So here's where we get into light being something altogether different, new, and interesting. Light does not need a medium to travel. Light does not need a medium. Light can travel right through outer space where there's really essentially a vacuum. There's no gas or solid or liquid for that light to oscillate. But we know that waves oscillate something, so what is light oscillating if it's not matter?
Energy? No.
Well, light transmits or communicates energy, just like sound waves transmit energy. Joshua?
Because it's electromagnetic.
Ah, okay, so that's exactly, it's oscillating a field, an electromagnetic field. So light oscillates a field. And none of my markers are going to work. Let's see if I've got an extra. red's not like my color of choice, but we'll go with it. It oscillates a field, the electromagnetic field, in fact. And because it essentially sort of has two components, right? There's electrical component and the magnetic component of the field. They just work to regenerate and re-energize each other. So they don't need a medium to travel through, and they don't die out. Like sound can only go so far before the amplitude decreases and decreases until it's gone, right? I mean, I can't hear what somebody just said in India. Sound just doesn't travel that far. But light does. Light travels, from the sun to the earth over huge distances, over huge speeds, and, it arrives here. And what's happening is transverse waves travel in a direction, and they oscillate perpendicular to that direction, right? Like longitudinal waves oscillate in the direction of travel. Transverse waves oscillate perpendicular. Right? So if the direction of travel is like this, the oscillation is up and down, perpendicular to that, right? And the electrical component and the magnetic component are also perpendicular to each other. So we've got this right? Like this. I can't do it. I'm not coordinated enough. But we've got an electrical component going one way and the magnetic component going the other way. Yes. So if the direction of travel is like this, I guess that's kind of an easier way to think about it. So they're perpendicular to each other and the direction of travel. And there's kind of a picture in the book there. And the electrical and magnetic field regenerate each other. So you don't need a medium. They can just travel even through a vacuum. So, compared to sound, is light faster or slower?
Faster.
Much faster. And we know that sound travels faster or slower in a solid versus a gas.
It travels faster.
Faster. So how about light?
Oh, I thought you were talking about light.
Travels slower in solids.
Okay. So sound speeds up in denser media, right? Sound speeds up in a liquid versus a gas, even faster in a solid versus a gas, because it takes time to transmit that wave. Light actually slows down. So light is fastest in the vacuum of space.
Which is really good for us.
Yes, because we really want it to get here from the sun. And it slows down in air, but only a tiny bit. It only slows down just a tiny bit in air. It slows down much more in liquids and even more in solids. We actually really essentially mathematically consider the speed of light in a vacuum and the speed of light in air to kind of be the same in this class. Does anyone know what that is? The speed of light?
Oh, it's like 30 million,
300 million meters per second.
300,000 meters per second.
300,000.
There's like 6 zeros.
There's no in air. There's
It's 3 times 10 to the 8th meters per second.
there are 8 zeros.
Right. 1, 2, 3,
Wait, no, 39.
That's
Yeah, there are 8 zeros.
Yeah.
it's not.
Okay. Is that right? 1, 2, 3,
Yes.
6, 7, 8. Okay, 3 times 10 to the 8th meter per second. What was that? That was weird. So very, very fast. I just like scientific notation better. I'm not going to remember. And Einstein called this C in that famous E equals mc squared equation.
What's about light?
Energy is mass times C, which is the speed of light in a vacuum. So what this is squared. So what this is saying is that energy and mass are the same thing. Energy and mass are the same thing. Like, yeah, did your head explode? That's what that says. And it says that they are proportional to each other in relation to the speed of light squared. Energy and mass are the
C
same thing.
stands for what?
The speed of light. So the C in that equation is the speed of light. So if I use C, what I mean is the speed of light. And whether it's a vacuum or air, even though we know it slows down a tiny bit in air, we're just going to assume that that's 3 × 10⁸ meters per second, the speed of light. Now, if we're in water or glass, we're going to see that that speed was going to slow down.
I've done too much
So
talking
then
today.
would C be squared?
And
Or would the
equals
entire
MC
equation be
squared.
squared?
The C. And when you
Okay.
square a number like that, you square both the magnitude and the units, so you'd end up with meters squared per second squared. Patrick.
Are we going to measure the speed of sound outside, or?
No, I don't think we're going to have time today. It rained us out last week, and it's beautiful today. But there's so much to cover and so many fun things about light that are much more fun than sound. I don't know. You guys can do it. I know, y'all want to go outside. You guys could do it, like, on your own. Just get really far apart.
Doing an experiment.
And clap. Yes, you're there. And clap. Clap really loud. Like, or bang two things that are loud together, but don't pick metal things because they really echo and that throws you off.
That's what I said for pots.
Yeah, bang. No, pots really echo.
Like bricks.
It says rocks in there. I would clap because I clap really, really, really loud. But, I mean, like two big Lego Duplos or something plastic, something that's not going to reverberate like metal, probably. What evidence do we have that light is a wave? I keep telling you, light's like a transverse wave. Light's an electromagnetic wave. What evidence do we have to show that light is a wave?
That's what Clark Maxwell said.
Okay, we'll trust that guy who everyone says is really smart. And yes, I mean, I can kind of understand that way of thinking, and we can trust him. And one of the experiments that has shown that light behaves like a wave. So you guys remember when we played with the slinky, and we tried to show some wave interference, right? We tried to show that two waves, if they collide and their amplitudes match up, you're going to get one big wave for a second, and then they keep going. If their trough and crest meet, you get a flat point, and then they move on, right? Wave interference definitely happens, right? So, like if I take a beam of light, and lasers are beams of light that are single wavelength. So single wavelength light is useful for experiments. If I take one beam, I shine it, there it is. If I take two beams and I shine them, right, then I just get two beams of light, right? But hopefully I can get this to work. It's really helpful to do this in a dark room, but we might not have that option today. Maybe we'll have to go to a dark room next week.
Machine.
So if I shine one beam of light, then I get one little pinpoint of light.
There's a closet over there.
Yes, we can pack into the closet, but
I heard something
hopefully
ticking
not.
in the big closet, and I don't like the big closet
We don't like
anymore.
the big closet. So will you aim the camera so I can try to... if you shine one thing of light, you get one beam of light. If you shine two lights, you get two pinpoints of light, right? So think of things we know are waves, like water, right? Think of water. If it passes through a hole, right, and it has to squeeze through like a little slit, waves form, right? Or if you drop a rock, waves form in the water. If you drop two rocks, the waves form, but then when they collide with each other, you get interference patterns, right? You get crest and crest meeting, trough and trough meeting, and you get kind of this place where waves meet. Well, if light is like a wave, it should have interference patterns just like water. So if I pass, one beam of light through one slit and one beam of light through another slit, I should get just two beams, right? Like, and these lasers, I can't manage to get a laser to pass through two slits because it's so small, I can't cut slits close enough together. But this is also monochromatic light, one wavelength of light. If I pass it through two slits, hopefully we can...
Do you want me to bring the camera over?
Maybe, yeah. Hopefully
You're
we
getting
can
two
get
lights,
it
I
to-
can see them.
I'm getting two lights. That's not what I want to get. her. Can you see? You might all have to come up, or I might have to see if I can hit the desk. Light is really pesky. Well, but it's just two. I'm not getting all of the ones I want.
Should we get any more?
Yeah. Oh, there we go. Right. So two slits, one light beam. More than one tiny amount of light. Oh, wow. And that's wave. That's wave interference. If you pass light, and you see like lots of spots. See all the little speckles? Right? Two beams of light should just
Four?
make,
Oh, 8.
or lots.
What?
Yeah.
I think it's reflecting or something.
No, it's a wave interference pattern, and it's
Why does it do that?
well because light is a wave. When it passes through two slits, it spreads out like a wave. Right, two slits. I don't know if I
I
can
know.
draw this, but so when light passes through two slits, at like my drawing skills are just really not good enough for this. So it'll pass through two slits, and so we've got waves. They hit the two slits, and they spread out like waves. But the places where those waves collide form these interference patterns. See the little checkered area? Where you get no wave in some places because they destroy each other, destructive interference. And you get big bright wave in some areas where they build each other up, where their amplitudes collide. So we can see that light is a wave even with just a piece of paper and a monochromatic beam of light, just because they make wave interference patterns. But that's not the whole story about light either. Light has these wave-like behaviors, but it doesn't always behave like a wave. And in fact, it behaves kind of crazily sometimes. So let's think about what else we've got. Light sometimes behaves like a particle. Light can behave like a particle. Wave. So light behaves like a wave, and we see that because of it does wave interference. Right, like that drawing. I mean, maybe the book has a better drawing than that of this phenomena. It's hard to draw. If you watch a YouTube video on it, it will show it with water, and you can see it, and then you can see it with light again. It's much easier to see. And hopefully we can get a dark classroom next week, and maybe I'll try to do it again. But light is also like a particle. All right, so does light have mass? I see heads going.
No.
No, light does not have mass.
It's like throw it all in the box.
Nope. Air has mass, but waves, like sound, don't have mass, and light doesn't have mass. So that makes it kind of like a wave. How can you have a particle with no mass? That's crazy and ridiculous. People did not want to believe this. But, and I can't reproduce this experiment for you, but what they found was if you shine light on a piece of metal, and the light is at least the right frequency, this, like the very moment the light is switched on, with no time delay, it knocks electrons off the piece of metal. And it's kind of analogous to like say I lined up cans and shot them down with a BB gun, right? If a BB hits the can, it knocks the can over. And it's like you shine the light on the piece of metal and the electrons go flying off like they've been struck by a particle. And even the pattern at which they're scattered is like they got struck, bombarded with tons of tiny little particles, and they go scattering off. So light behaves like a particle. That's called the photoelectric effect. It's a property of metal. Light behaves like a particle, and we can put light in situations where it really does behave like a particle, but we can also see that it behaves like a wave. And so this was really baffling to people. And it has properties of a wave and properties of particle. So light doesn't have mass, but when it collides with something like metal, it knocks electrons off. And we can mathematically predict the energy of those electrons, how many electrons, what wavelength of light we can use for what particular metal. So this is clearly something that isn't a fluke. It really happens. And it's different for each type of metal. It's different for each energy of light. We can make these predictions. So light behaves like a wave. Light behaves like a particle. And so here I'm going to give you some advice for test taking. There's a test question that just kind of says, describe the current thinking about light. And do it in detail or something like that. So I want to be really specific with you guys about what, I'll do that for you so you can write. What does it mean? Like, describe this and do it in detail. So there are certain things that your answer really needs to have. Okay? Joshua.
Does the question want the three theories?
Yes. So what do you think?
About what?
All three theories?
Yeah.
So there's the quantum mechanical theory, there's the light wave theory, and then the particle theory.
Okay, what is quantum mechanical theory?
It says that light is a wave particle.
Okay, so
Tiny packets of waves. Right.
all right, light is tiny packets of waves. So yeah, it's something like shooting BBs, except those BBs are made of tiny little waves instead of matter. Right? Light is not matter, but light comes in discrete packets, in quantized amounts. Every photon, right, these tiny packets are called photons, and every photon has a specific energy. That's what defines it. And then the wave theory, light is a transverse wave. And the particle theory. Okay, so key points, key words that I want you to have in an answer like this. Something about the wave has an electrical component and a magnetic component, or it's an electromagnetic wave. And that light has a wave-particle duality. Particle duality. Meaning it does have qualities of a wave, it does have qualities of a particle, that we don't think of those things as being something that one thing can have, but it does. So if you work these two things into your answer, you're going to get full credit. This is a confusing test question, and those are really the key important points that I want everyone to take away about light. Light does behave like a particle, and it does behave like a wave.
So it's a particle wave?
Yeah, I mean, it's a photon, which really is a particle wave. For me, I think the quantum mechanical description of light is the most accessible to describe all its properties. But who knows that we'll find something even better. I don't know. I think that's pretty good, actually. Where are we? Okay, we're there. So pass out filters. There is a puddle of water. I don't know what it's caused from. It's just water, though. It's not dangerous. And, so every few people can share a little filter. This is the same thing, you guys. It's just in a little box, but it's the same thing. I don't know. It might be easier to look through the other end. So if you open up your little packet there and you look through that, what are you going to see? Lots of different colors. And why? Share them around once you've looked. He's got something. And also, I want you to point it and look at one of these interior lights and then point at the window and look and see if you see a difference. Oh, fun. I have one too. We can do that thing with two of them.
Walking around with this and just like pretending it's like.
We're having happy rainbow moments. Can I look through it? I haven't looked at these lights before. Yeah, I mean, these lights do have a pretty wide range of color. If you only look at like an incandescent light bulb, you really don't see every color. But these fluorescent lights are pretty good.
The colors are thinner apart when you're looking in the room, and then you go look out the window, they're like big and thick and bright.
Yes.
They're everywhere.
It has something to do with the different amplitude more than the different range of colors.
Look funny.
I wonder if it's right. Oh.
I know what I'm trying to do.
I see that.
You have to look like down. It's like there.
I mean, you guys can pass around.
Stop putting your fingers on the edges. Keep your fingers on the edges.
Versus.
I forgot my rule.
I'm going to look and
Walking around with
see. One problem that you have, I know my phone's not a full spectrum bulb,
Then I would have a massive headache. Oh, look at the lights in the ceiling. Whoa, look at my
What are
hand.
those great contact lenses that did that? That would be like. And what if you put them on your friend when he was asleep, and then when he woke up, like all the lights were on, and he's like, "What?"
I think light is a transverse wave. No amplitude.
Wait, what?
Quantum mechanics. Light.
Oh, while we fool around.